All right, let's start. I guess maybe some people will arrive. Probably many people are in vacation because next few days, I think Friday and Monday are probably vacation. But oh well, maybe they'll follow from YouTube. So today, what we will do? So today, actually, it's quite a shame that most people are in vacation because we're gonna kind of present this framework I've prepared. It's very simple. Okay, don't be scared. It's in Python, just to help you easily implement your own cellular automaton with minimal boilerplate code. So we're going to start by presenting this, and then we'll finish what we started last time. So we're going to speak about one of the few theoretical results about cellular automata. And we'll see. If we have time, we'll begin also with the next course, which is just starting and presenting different discrete cellular automata. And then once we'll be done with the discrete ones, we're going to go to the continuous ones and so on, but probably not today. So last time where we left off, we were talking about these Wolfram classes. So just to make a summary. So Wolfram conjectured these 4 classes essentially by looking at the behaviors of mostly one-dimensional cellular automata. And so this classification is nice if we could actually use it effectively, because that's essentially what we want to do ultimately, right? We want to have a classification that, given some set of rules, or more realistically, given some videos of the dynamics, we are able to tell kind of rigorously if it's interesting dynamics, if they are actually complex, or if it's just something which is not very interesting, where you could not have life emerging. So just to remind you, these 4 classes, so we have class 1 and class 2, which are very similar, which are essentially the classes which are very predictable. So very quickly, you get something which is either completely static or periodic with a small period. So these are class 1 and 2. Then you have class 3, which is the total opposite. It's something which is completely unpredictable or seemingly unpredictable, right? Because don't forget that all the cellular automata, by definition, they are completely predictable if you know the underlying rule. But what I mean by this is that if you look at it without trying to go into the details, it looks completely random or chaotic. So this is class 3. Then class 4 is the one which is kind of in the middle. So it's an equilibrium between randomness and structure. So you recognize some things which are kind of predictable, but over the long term, it's really unpredictable what will happen because the interactions are very complicated. Right, and so the idea of Wolfram is that if you have something which is class 4, so essentially something that looks complex, it is actually as complex as it can be, in the sense that it is Turing complete. All right, so that's where we left off last time. And so we presented these 1D binary CAs, the elementary cellular automata. So you might ask, okay, among these cellular automata, which ones are class 4? So which ones are actually interesting? And there are 2, right? So these number of the rule is recall the Wolfram numbering scheme. So there is rule 110, which is probably the most famous one. And as you can see, okay, you voted last time, you voted it for the most interesting one among 2 others. And we can see, even from a single pixel or from random initial conditions, that we have these kind of streaks that form. So these we can identify as something, some kind of deterministic structure, but then they have non-trivial interaction. So when they collide, then they may change direction, they may merge, they may create more things. So you have these non-trivial interactions. And then you have rule 54, which is interesting because if you start with a single white dot, you wouldn't say that it's a class 4 rule. Like here, it's clearly class 2, completely periodic and predictable. But if you start with random initial conditions, then you get these beautiful patterns here with some streaks again that can interact. And so people believe that the rule 54 is Turing complete as well. It's not proven, whereas rule 110 is proven. And when I say proven, remember, is with the caveat that proving means constructing a Turing machine with some acceptable interpretation. And this what we mean by acceptable is not well defined. But when you see it, you are convinced, essentially. So rule 110, by the way, yeah, I sent you an email to give some feedback. So if you can, please take the time to do that. Some people already did it. And somebody mentioned the fact of having the notebook in advance would be nice. So I will try to do that from here on out. So if you go on the website, you will have the notebook that I will use in class. And so this notebook is on the website if you want to follow along. Okay, that's it. So yeah, so rule 110, so this one here, has been proven to be Turing complete by Matthew Cook in 1998 and then published by 2004. And if you look at the story of this, it's kind of funny because there was a bit of drama because Wolfram claimed that Matthew Cook revealed some non-disclosure information and then he prevented him from publishing and then, okay. But in the end, it was published in 2004. And how did he prove that it was Turing complete? So what did he do? Well, as usually, just constructed a very simple Turing machine inside the cellular automaton. But it actually was not a Turing machine. It was some kind of proxy for a Turing machine. So he used these gliders, so these kind of streaks of triangles. First, he studied them very extensively. So he looked at every pair of gliders, what happens when they collide. Sometimes they're just like translated to the right. Sometimes they're annihilated. So he looked at the gliders and then at their interaction, and he built some kind of basic logic gates with these gliders. But instead of building a Turing machine, because it feels very hard, right? We just have access to one dimension. It's hard to do it like in the von Neumann where you have the actual reading head, etc., because we are in a one dimension. So instead of building a Turing machine, he built something which is called a tag system. I don't know much about that, but it's an even simpler system of computations, which is essentially in one dimension. So you have some zeros and some ones, and then you can add or remove zeros and ones at both ends, and you can do computations with that. So he decided to actually implement this thing, which was more appropriate for his system, and he managed to do that. And okay, you have the tag system, and people proved by another construction, which I'm not aware about, that the tag system is Turing complete. And so if you can do the tag system, then you can use this tag system to do the Turing machine. So the cellular automaton is itself Turing complete. So that just to give you an idea of how people prove that things are Turing complete. So far, I haven't seen any other proof which is simply construct the Turing machine. And I don't think there can be any other kind of proof. Right. And for the second one, as we said, rule 54 is believed to be Turing complete, but no proof has been produced, probably because it's super tedious. I think if somebody decides to do it, you probably could do it. And that's pretty much it. So as far as I know, there are no other rules which are considered class 4 in this elementary cellular automata. But I mean, it could still be that for some specific kind of initial conditions, for example, you decide to put one live cell every 3 cells or something like that. Maybe if you prepare some initial condition which is kind of peculiar, maybe this will induce some class 4 dynamics in some cellular automaton, but we don't know about that. People mostly look at random initial condition. And when I mean random, I mean uniformly random in black and white. So, right, but let's not forget that the whole reason that we want Turing completeness is not just for being able to do computations inside the cellular automaton, because that is useless. The reason we look for Turing completeness is because we know that it's kind of related to self-reproduction, right? But you have to be careful, because as we saw, Turing completeness implies self-reproduction for a certain choice of output and representation. And remember, there was this notion of real self-reproduction versus false one. And so in this case of rule 110, we do have a Turing complete set of rules, but I think you do not necessarily have self-reproducing creatures, simply because the output of the Turing machine is kind of an abstraction layer. You have to interpret, okay, there is a glider here, so this is a 1, etc. It does not mean that you even have a kind of a constructing arm that you can build, right? The possibility of building a constructing arm is not necessary for Turing completeness. You just need to build some kind of representation of a constructing arm, which might construct in this abstract space, not in the actual CA space. So in particular, for the rule 110, I'm fairly certain that you cannot have universal self-reproducing creatures, simply because I don't think you can build some kind of constructing arm. For example, you always need this kind of background here. So I don't know. So you definitely have self-reproduction in the sense that you output a representation of yourself. I am not sure that you can actually duplicate yourself, right? And this does not guarantee, the Turing completeness does not guarantee to have the actual self-reproducing creature. Okay, any questions about this? That's good. All right, so I just want to be careful with that, because usually people say, oh, it's Turing complete, it's fine, we have self-reproduction. Actually, not really. And today we'll see a way that we might be actually able to prove that there could be no constructing arm in some sense. So let's discuss a bit. So I think we didn't discuss this last week, right? The limits of the Wolfram classes? I don't think so. So yeah, as we said, having a universal classification system for a life would be very nice. But the current proposal of Wolfram is not satisfactory in this sense. Why is that? So the main problem is that the definitions are extremely fuzzy and up to interpretation, right? It's not at all rigorous. So it essentially, if you were to apply it as Wolfram stated it, it would essentially mean, okay, just look at the dynamics. If it looks complex, then it probably is. So that's not very satisfactory. And how would you even go about automating the search for class 4 systems? So so a few points that some people raised also actually in the very first course. So for class 2, the periodic systems, so given finite space, so a finite size for the cellular automaton, all dynamics are periodic, right? Because you have a finite number of possible configurations. So if you run it long enough, it will eventually loop back to a configuration that it was already in. And when you're in this point, since the dynamics are deterministic, you go into a loop, right? So according to kind of the definition of class 2, which is periodic dynamics, every cellular automaton is periodic. So they are all class 2. But actually, no. So okay, by class 2, what do we mean? We mean quickly periodic. So if the period is of the order of the number of possible states, we wouldn't say that it's class 2. So for class 3, again, the problem is that we say, okay, random dynamics, but what does it mean to have random dynamics? Because all dynamics are completely deterministic and not random at all. So when we mean random, we mean looks random. And the same thing for chaotic. So the idea, usually when we say chaotic, what does it mean? We mean that by a very small change, you will have a very big difference in the future, in the trajectories. But here again, this is not well defined because we have a discrete system. So what does it mean to make a small change? You need to change a whole pixel, right? You cannot slightly change a pixel. So this change cannot be made arbitrarily small. So even chaotic is not well defined. And for class 4, obviously, okay, the class 4 inherits all the problems of the other classes because it's defined as a complement of the other classes. So, and of course, this classification does not discuss the dependence on initial conditions. I actually tried to look in Wolfram's book if there was any precision on what initial conditions he considered, and I haven't found a discussion about this, so it's kind of unclear. All right, so people were unhappy with this, and so in the math point of view, some people try to address this by making a rigorous kind of definition of these 4 classes. So this was Kulik and Yu. I don't know if it's pronounced like this. So they tries to formalize this classification in this paper. And the definitions are as follows. And of course, they try to choose rigorous definitions that kind of captured the intuition of the Wolfram classes. So instead of defined 4 separate classes, they defined nested classes. So you have class 1, which is included in class 2, included in class 3, included in class 4. So class 4 in this case is all cellular automata. And so if you want to connect this back to the Wolfram classes, you would just say that class 1 for Wolfram is class 2 for Kulik minus class 1 for Kulik, right? So Wolfram class 1 is everything that is in here and not in there. And similarly, class 4 is everything which is not in class 2, 1, 2, 3, right? Okay, that's just a matter of conventions. It's just easier mathematically. So one of the big things that they need in this definition is they need to have at least one stable state in the cellular automaton. Okay, so what does it mean to have one stable state? So a stable state is a state which, when it is surrounded by other stable states, it remains in the same state. Okay, so it's kind of very intuitive. So if you have, for example, let's say the stable state is 0. So if 0 is in a neighborhood of other zeros, it will just remain 0. So this state, you can kind of see it as the vacuum. So when there is nothing, of course, nothing can come out of nothing. And so that's it. But the stable state is not guaranteed to exist for any cellular automaton. Okay. So let me make a very simple example. I take the cellular automaton, which has a neighborhood of just himself. And the rule is that you change your state at each time step. So there is no stable state, right? The 0 goes to 1 and the 1 goes to 0. So that's one thing that you need, that in their definition, Kulik and Yu ask. So if you don't have any stable state, you are automatically class 4, which is not great, of course, because I can devise, the cellular automaton I just told you is just something that goes from black to white, black to white, black to white. And this is formally class 4, according to this definition. But okay. So why do they require this stable state? And the reason is pretty simple. It's because they need this notion of S-finite configurations. So S-finite configuration is simply a configuration which, okay, technically they look at infinite configurations. Why do they do that? Because you have this problem that otherwise everything is periodic. So they look at infinite configurations, but they look at configuration which only a portion of the configuration is non-zero, non-stable. Okay. So an S-finite configuration is a configuration which is everywhere stable, except in a finite number of places. So essentially, they put a bit of stuff in the middle and all the rest is vacuum. And so they can say, actually, this is infinite, but I have a finite amount of stuff when I begin. All right. So how do they define the classes? So class 1 is is the cellular automaton which have a stable state and for which all S-finite configurations eventually evolve into the homogeneous stable configuration. Okay, so you begin with any configuration which is not infinite, and then in a finite amount of time, you get the homogeneous configuration. So everything dies out. So class 2, very simply, it means that for any S-finite initial configuration, you get periodic behavior. So here, crucially, the periodic thing actually matters because we technically have an infinite grid, right? So not every configuration will be periodic. So now it makes sense to say class 2 is the periodic ones. Then we have class 3. Class 3 is a bit more complicated. So for class 3 are the automaton where it is decidable, so it is computable with a Turing machine, which always halts, whether a configuration C1 evolves into a configuration C2, where C1 and C2 are two S-finite configurations. So what does this mean? This means that, okay, you give me two configurations which are finite. I can compute something and tell you for certain that C1 evolves into C2. If C1 evolves into C2, okay? And this is kind of, okay, the first two ones the first two ones are quite intuitive. They're very similar. This one is very dissimilar from the Wolfram one. And we'll see why they define it like this. And then class 4, as we said, it's all the nested classes. So class 4 is all the cellular automata. So yeah, so there are many problems again with this formalization, but at least it is rigorous. And the first problem is this question of the stable state that I already mentioned. Yeah, and this is the example that I mentioned. The automaton that simply flips each state into its opposite has no stable state. Yes, a question.
Why would it ever be undecidable if our CA is specified in terms of these very local rules? And I mean, it's a very clear procedure to decide whether or not what happens, right?
Well, not necessarily, right? Because you don't know how much you need to evolve your automaton, right? So let's say you have C1 and C2. You don't know if you missed C2 and you cannot come back, right? Your automaton might do something like this, and then after 100 million steps, get to C2, right? Exactly, and this is important here again, that we have an infinite kind of state. If the state was finite, the world was finite, then it would be decidable every time, right? Because you can just check all the configurations and yeah. Right, and then I have another problem which they don't mention in the paper. Quite strange. So class 2, you would like to put inside all the periodic things, but there are some which do not belong in class 2, which I feel they should. So tell me if my reasoning is wrong. But for example, let's look at these dynamics here, right? So these dynamics are very simple. So every white pixel, it just goes to the left forever. And so you see that this, if I start with an S-finite configuration, so a bunch of stuff in the middle, it will just translate to the left forever. And this formally is not periodic, right? Because the state is always different. You take this state, then you have this state, then this state, then this state. So technically, this cellular automaton does not belong in class 2, according to this Kulik and Yu. And actually, to make sure, because this seems strange, for me it would be better to define periodicity up to translations, which would put this one into the periodic ones. But they specifically say, if I read correctly, that translation do not count for periodicity. But oh well, okay. So many problems with this configuration, but we're gonna go on to the most important problem. Right, so this one is class 3, because it is easy to tell if you give me two configurations, I know if this one will go to this one, I just have to see if they're kind of spaced apart correctly such that one translates into the other. Okay, so these are some problems, but maybe they're not too important to mathematicians because they just want a nice definition, etc. But then you get this. So they show in their paper that it is undecidable in which class an automaton belongs to. So okay, you have these super rigorous classes. You're super happy because you don't have ambiguity. And now actually you cannot decide whether an automaton is one of these classes. So they're essentially useless again. Okay, I'm not going to go through the proof because it's kind of involved and I don't know it precisely. If you're interested, you can look at the paper. But this is somewhat expected. And okay, this is not a proof, it's just how to build an intuition. So we know there are two incomplete automata, right? So in some sense, we should not, it should be undecidable to know the future of an automaton, because if we were able to kind of know the future infinitely far, we would solve the halting problem, right? And so when you kind of try to ask whether an automaton is periodic, you're kind of asking me, okay, if I simulate this for infinity, will it be periodic at some point? And so you kind of ask these questions, which are very similar to the halting problem questions. And that's why you should expect usually for these questions to be undecidable. And indeed they are in this precise case. So for this reason that I just said, we should accept that any meaningful classification will usually be undecidable. And that's something that Wolfram likes to say, likes to call the principle, how does he call it? The principle of computational irreducibility. So it means that Wolfram's principle of computational irreducibility, which means that you cannot know what will happen to the automaton except if you actually simulate the automaton, right? And so it is essentially a rephrasing of the halting problem, you cannot know what a Turing machine will do without actually running the Turing machine, right? That being said, this does not mean that there cannot be good heuristics, right? So for example, our intuition when we see the dynamics of the cellular automaton is obviously not rigorous, not perfect, but it's a very good heuristic. So it seems we have a good intuition to be able to tell whenever a cellular automaton is interesting or not, right? So one should look for, not for precise classification that are completely rigorous, one should look for heuristic methods which seems good. So methods which are not exact, but which will allow you to kind of sift through the cellular automaton quite easily and fast. So I did not mention, so why do they use this for class 3 instead of like chaotic behavior? So class 3 definition is chosen so that class 4 minus class 3 are the Turing complete automata. So what do I mean by that? So essentially, they don't choose class 3 to be the random cellular automata. They choose class 3 such that whenever a cellular automaton is Turing complete, it's not in class 3. Okay, so it's kind of convoluted, but if a cellular automaton is Turing complete, it is clearly undecidable whether C1 evolves into C2, because this is the halting problem. And so you know that when a cellular automaton is Turing complete, it will be in class 4 and not in class 3. And so the reason they chose this, essentially, they mimic the Wolfram classes by saying class 1 is like the Wolfram one, class 2 is like the Wolfram LAN, then class 3 is what I need to have such that class 4 are the Turing complete ones. Okay, that's just a curiosity, it's not very important. But in particular, it does not correspond at all to the random cellular automata, right? Because this one is in class 3. Okay, any questions about this? Okay, good. So now, let's go to the practice that I was mentioning before. So I will show you, let me see here, what do we have? Yeah, so I have this thing here, which is already ready. So if I run this, just to show you what it can do, I hope this runs while I'm streaming because it's kind of heavy on the computer. So let's see. He's struggling or? Oh no, wait, 1 second. Yeah, he's struggling a little bit. Let me close a bit of stuff. Okay. All right. Oh wait, this is the 2D cellular automaton. Okay, so let me go to the 1D. Sorry. Tac. Right. So let me comment this. So it will be clear right away, right? I'll just go through this code very quickly, just to get an idea of how it works. So if you want to implement something, you will see that it's very easy. Just has trouble launching, but. Okay, so here we have our window. Here we have the initial conditions. And then I can simply run with space. And we get the dynamics. I can stop with space. I can delete to restart. And I can also change the rule kind of on the spot, right? So here I'm cycling through the CA rules. And all of this, to do all of this, you just need a few lines of code. All the boilerplate, like the visualization, etc., is all done for you. So let's go through it and see how it works. So I think it's very simple. So all you need to care about is you have this main.py. Okay, this is the thing you should run. And so what do you need to do to run an actual cellular automata? So the way to do this is this. I define for you this class, this automaton class. Okay. And this class is what you will use to code a new automaton. Okay. This class is very simple. It does almost nothing. So it has, by default, okay, it knows the size of the canvas that you're using, so HW. And it has some tensor here, the world map, which carries the representation, so the visualization of your automaton. Okay, so this is a tensor which is 3HW. These are the dimensions of the tensor. So what does this mean? We have 3 colors for each pixel of the screen. Okay. And then all you have to do is define the step function and the draw function. That's it. And then you can add some interactivity if you go to process event, if you want. But that's all you need to do. So let's look at what it looks like for the 1D cellular automaton. Okay, so let's see it. Okay, so here we have. So you start, and here I have an extensive documentation for this class. So if you don't remember everything, that's fine, don't worry. So we start by defining our new automaton, okay, and we inherit from the automaton class. All right, so that we get all these predefined functions, etc. So here I define the initialize function. So for my 1D CA, what do I need? Okay, I always need the size of the world that we'll be using. And then for 1D CA, we'll need the Wolfram number that determines the rule. And this is just a Boolean to know if we want a random initialization or not. Okay. Then I start by initializing the superclass, so just the automaton. So this is a line that you always put. And then below here, I do what I need, right? So here there are no more constraints. You do whatever you want, right? So in this case, I need to convert the Wolfram number to an actual rule. So we'll see how we do that. Then we prepare our world. The world of our automaton will be just a vector of W elements, right? Because it's a 1D CA, so you just have a vector, a one-dimensional vector of elements. And then we need also the time to know at which time step we are, right? In the evolution. Okay, and this, don't care too much about this. Then all we have to do is define our step function, right? So let's see how we do that. First, let's look at this convert Wolfram number. Okay, so when we get the Wolfram number, remember the numbering. The Wolfram number is just a number from 0 to 255. But if we want to use it, we need to convert it to binary. So that we can, so let me pull up the picture that I had, which will make it more clear. Yep, here. I think, it was not here. Right, so where exactly? So we need to do this kind of procedure, right? So we get this number here. So all I will do, my goal is just to convert this number into a list of ones and zeros according to the binary conversion, okay? So you can do this in a million different ways, whichever you prefer. This is kind of an efficient way. So this is just, so by the way, if you're not familiar with PyTorch, tensor, when I say tensor, you can replace in your mind by array or list or whatever. It's exactly the same thing. So here, I will store the output of my rule, which is translated into zeros and ones. So I just prepare my array, right? Prepare, is this readable? Yeah. My array of 8 binary elements, okay? For now, it's just zeros. And then what do we do? So this is kind of, okay, you might want to do it with modulo 2, and it's perfectly fine. This is kind of a very quick way of doing it. So here I have the Wolfram number. This operator is the right shift. So this means that I shift the binary representation by 1 to the right. And here I just take the first bit, okay? So for example, if you're not familiar with this operator, which I wasn't before implementing this stuff, for example, if I do 101 and then right shift it twice, okay, this would mean that I take this number and shift it twice to the right. The number which are rightmost, they just disappear. So this will give me 001, right? So we shift 1, then we have 1, 0, then we shift again. And then when I do AND 1, it just means that just keep the first bit, okay? So this is 1, right? So essentially here, for I that goes from 0 to 7, we first shift once and then take the result, then shift twice and take the result, and we store this in our array, okay? So now the array out contains the binary representation of the Wolfram number, okay? So don't stress too much about it. You can do it in many different ways. You can do it by doing integer division by 2, then by 4, then by 8 to know which of the numbers are 1, but okay. Here now we have array of 8 elements, which contains where out E is equal to 0 if the neighborhood number E yields 0, right? That was kind of the way that we defined the rules. Okay, perfect. So now we store this kind of processed rule into our attribute here, self.rule. And now let's see how we do one step. So you see the step is really 3 lines. So it's really not that complicated. But we would like to do it in parallel. Okay, so one way to do it. So here I'm being very pedantic. Depending on how familiar you are with Python and PyTorch, it might be useful or not. So one way to do it, which is not parallelized, would be as follow. Okay, very intuitive. So for I in range 0 to self W minus 1. So we just iterate over the cells, right? The new state of the cell will be, we first compute the neighborhood, right? So we need to look at the cell to the right and to the left. But crucially, we need to understand which of these 8 neighborhoods we are, right? Remember, the neighborhoods are numbered. Okay, so how do we tell in which neighborhood we are? That's very simple. So we look at the 3 elements, okay? And then we look at the representation in base 2. Okay, so for example, here we have on, off. What is this number? Is the number 0, 1, 1 in base 2. And 0, 1, 1 in base 2 is equal to 3. Okay, so this is neighbor number 3. So that's what we need to figure out. So how do we do that? Well, we do self.world. So this is the one to the left, I minus 1. This one is times 4. Why is it times 4? Because it's the 3rd digit in base 2. So it's 2 to the 2, so it's times 4. Plus ourselves, which is times 2. Plus the one to the right, which is times 1. Okay? So this is neighborhood number. Okay. I'm sorry. So in this variable, I have the number of the neighborhood, which precedes cell number I. And now all we need to do to update the cell is just use the rule, right? So we use self.rule, and we say, okay, the new state of the cell is the one that corresponds to the neighborhood number. Okay, so this works perfectly fine. Okay, actually you need to be careful because here you will have some problems at the boundaries, but you can just put a modulo self.w and then you'll be fine. And also you must be careful to not modify the world as long as you're using it. So you should store this into a new world, etc. But essentially that's all you need to do. Okay, the obvious problem with this is that we're not exploiting the fact that we have a cellular automaton. We are iterating over the cell one after the other when we could update all the cells at once. So how to update it? How to do it all at once? And that, depending on the system that you're considering, it might be very obvious or very complicated. So in that case, it's reasonably easy. And I use PyTorch. If you use NumPy, it's exactly the same. you should use one of these libraries which allows you to do kind of vector sums, right? So that's what we'll do. So how do we do that? So we need to write this formula, but obviously we don't have access to the specific cell each time because we do all the cells at once. All that means is that each time that I need to access the world with sum in some other place, I need to make a new array that contains these other cells. Okay, so let me be clear here with the example. So here we need self.world I minus 1, right? So what I do is I take my full world and I shift it by 1. Okay, so what does this do? Maybe here it will be useful to write on the board for people who are a bit unfamiliar. So let's say that we have, let's say that we have our world which is equal to this, right? Okay. So when you look at this one, okay, you need to look at the one on the right itself and the one on the left. So that's what we do in the for loop. Okay. Now we want to do it all at once. So to get a tensor that is always the one on the right, what I will do is take this one and shift it to the right. So here I will have this new tensor, 0, 1, 0. So is this one shifted to the right? And you see now, when I look at this position in the arrays, I have the element itself and the element on its right. And then I take one other and I shift it also. So I have this one. Okay. So now if I look at element I, we have I here. This one is I minus 1 and this one is I plus 1, right? So for example, if I sum these three tensors, you will get the sum of the neighborhood elements. Okay, so that's all we do. So we know that this part here will be the element shifted 1 to the right. So all that this do is shift the world 1 to the right. Then I multiply by 4, just as before, right? Then I add myself, just as before. Self.world I is just self.world, multiply by 2. And then for the third one, I plus 1, we shift it to the left and multiply by 1. Yes. Thank you. Okay. And so what happens here is that this sum of these 4 elements is done all at once in parallel on the CPU or the GPU. And it will be, if you run it on the GPU, it will be on the order of like 100 times faster. If you run it on the CPU, it will be on the order of 20 times faster than this. Okay? So what I always suggest to people, I mean, depends how comfortable you are with this parallelization, but usually it's easier to kind of think about your model in the traditional way. You just do everything sequential, and that's fine, because this is much more intuitive to write. Then once you have written that, you can start to think, okay, how can I do this in parallel? And then you have to do these kind of little tricks. Okay, great. So this is a vector that contains the number of the neighbor for each cell. So now how do we update? Well, we can also update all at once. So this is a trick from PyTorch. Or NumPy. So here I take the rule and I index with all the indices that we found, and this will make a new array with the results of all these evaluations. Okay? So this is the same as for E in range. Let's use list compression. This is the same as rule indices I for I in range W. Okay? For each index, we apply the rule and we store it in the array. And finally, we go forward in time by one dot. Okay. So this is the step function that you need to define. And then the last function that you need to define is the draw function. Okay. So the draw function is very simple. So we have our world, which we decided to represent here as an array of integers, which are 0 or 1. But now we would like to visualize it. Okay. So the way I set it up in my library is that you need to, sorry, it's here. Yeah, you need to define this self._world map. Okay. So self._world map is a 3HW tensor, which should be seen as an RGB image. Okay. So this world map by default, it's already defined. It's a 3HW tensors. So it's a three-dimensional array. And these three colors are between 0 and 1, and that's the image. So you need to kind of say how you want to draw your state. So in that case, it's quite easy. Okay. So we'll use the height dimension as the time, and then the width dimension is just the state of the system. So here, what do? I update the world map, and at the height equal to the time, right? So this means that I take the height equal to self.time, modulo h, so that we loop back up, but that's fine. And this, I put it equal to the world. Okay, so here I am doing some shenanigans because self.world self.world is a WH array, but we want to set a 3W array, so we should duplicate the world, right? So the world does not have the values for the RGB colors. It just has one value, alive or dead. And all I'm doing here is just I say, okay, if I'm alive, I will take the color 111. If I'm dead, I will take the color 000. And here, PyTorch does automatically for me. So it sees that I want to add an array with just one dimension to an array with 3 dimensions, and automatically it just duplicates the 1 dimension. Okay. So in this visualization, I choose to represent by black the dead cells and by white the live cells. Okay. So again, all these things are they're not super advanced. If you don't know about PyTorch, they might seem very strange, but you are free to do it however you want, right? And so once we have that, you can just go to the main, and here, okay, here we'll do a better job of showing you which things you should modify and which you shouldn't, but it's very simple. So here we choose the size of our window. Here we choose our target frames per second. Okay, I say target because I mean sometimes the computer is not fast enough. This you can just leave it alone, and then you just define your automaton, right? And you call it auto. So here we define a CA1D. We give him the size of the screen. We choose the Wolfram number, let's say 110. Okay, and this is for the initialization. Okay, I didn't show how I implemented it, but that's fine. And that's pretty much it. And then you can just, you don't even look at the rest of the code. You don't need it. It's just some boilerplate to show the picture. And now when you run the code, you should have your thing that pops up and executes. Okay. Okay, so here I printed the world state shape, and we have rule 110. Okay. So as you see, I can control it with the keyboard. And so I'll show you next how to kind of add interactivity, which is the nicer thing to have, right? If you need to relaunch the thing each time you want to change the automaton, it's very annoying very fast. So it's very nice that with this framework, it's very easy to just add interactivity right off the bat. Okay, but we should probably do the break. Yeah, so let's come back at 15 and 18 minutes. I hope, yeah. Oh no, I was not recording. Oh, that's fine. Up. Yeah. So the last thing I wanted to talk about this library, and then I think if you're interested, for example, if for your project you want to implement something, okay, you're allowed, of course, to make your own visualization library if you want. But if you want an easy way to implement something, you can even, because I included several automaton, and as we'll go over the course, I will add the code for the cellular automaton that I show you in this visualization thing. So we'll add also the von Neumann if you're interested. But let me just finish to explain how to add interactivity. And this is done through defining this function. So you have to respect the name of the function. So this function process event, and it takes two variables, so the event and the camera. Okay. So this method processes the events recorded by Pygame. Okay. So Pygame is the library that I use. So usually it's a library that lets you make games in Python. So it's very useful because it allows you to kind of view the things, draw on the screen. And the additional thing it does is that it records every event that happens. So each time you move your mouse or you click or you press on a keyboard, you have an event which is called, and you can choose to process it. Okay, and this is done through this function. So what do you do to add interactivity to your system? Okay, you have process event. So you have this event, and how you deal with this event is kind of annoying. So you have to go through the Pygame documentation, or you can just ask ChatGPT, okay, I want to, when the user presses enter, I want to do something, and it will just write for you this code. But okay, so what you do here is you first look for the type of the event. Here it's Pygame key down. So this activates when you press down on a key. And then further here, you look at event.key, which will be which key is pressed. Okay. So here I have just two possible keys. So I have pgame.key delete. So this is the delete key. And what do I do when I press delete? Well, it's very simple. I just reset the world. And I have defined for myself a function reset, which just sets the time to 0, sets the visualization to the black screen, and then reset the world. Okay. Very simple. And if you pressed N, so KN, it means the letter N. Pressed the letter N. Okay, we just pick a random rule. So we just pick a random number between 0 and 256. And I have created for myself, again, a method that changes the rule. So what does it do? Well, it computes, it processes the Wolfram number to get our tensor. And then it resets, I mean, let's actually see what it does. It doesn't do much. Yeah. It just updates the rule to the new rule with convert from Wolfram. So this function is kind of useless, but that's fine. And that's it. When you did this, now whenever you press N, this block of code will be called, and then you can add interactivity. Okay? And so here you might ask, why do you need the camera? This is because in the visualization I have made, you can also by default, you can kind of zoom in and zoom around. So let's see it. It takes a while to run. Come on. No. Because now I'm recording, it's struggling even more. Right, so here if you press Control and the mouse wheel, or Control and drag, you can move around in the world, right, and zoom in. And so the only reason why I pass the camera to the event function is just that now when you ask where is the mouse, it will tell you the mouse is on the upper right. But inside the world, the mouse is kind of there, right? So the camera, you will see, I mean, if you want to add interactivity with the mouse, like erasing stuff or drawing, you need to convert the coordinates on the mouse on the screen to the coordinates of the mouse on the world, and the camera as a function for that. So that's if you want to add mouse. So here I made, you don't have to make this function. I just like to separate the keyboard and the mouse. So you see here, I prepared like some snippet of code that you can reuse. So here we look, if we press down the button, we remember that the button is pressed. If we release the button, we know that we released. And then whenever we move the mouse, if we are pressing something, this X and Y will be the location in the world of when we are dragging our mouse, right? And so you see here we use camera convert mouse position. And so here you can add an interaction that you, when dragging with left click, okay? So let me just make you an example of what you would do. So let's say here, if event.key is equal to pgame.kc. So this will happen when we press the key C on the keyboard. So what would we want to do here? So here, let's say we have a self.color, which is a torch tensor 111. And let's say that this will be the color of our visualization, right? Because it's black and white by default, but it could be any color. Okay. So by default, it's a white color. And then when we want to change how we draw our system. So we go into self.draw. And here we'll simply multiply by the color. So here again, I have to do the shenanigans with the dimensions, but we will just multiply the world value by the color. And so this will tint kind of our world with a color. And so when I press C, what I want to do is just to take a random color. So torch.rand 3. Okay, 3. So this just makes a random tensor of 3 coordinates with values between 0 and 1, which is a random color. And so now if we go, if I didn't do any mistake, whoops. Yeah, takes a while to launch again. When we press C, we should be able to change the color of the visualization. Let me just see. Yeah. Okay, so we have our system. And now if I press C, I just change our color. Okay, so you see it's extremely simple to add interactivity to your thing. You can take a new and then, yeah, delete, start again. It's very simple to make very beautiful stuff with this thing. Okay, any questions about this? So the link to the repository where you can find the code is both on the notebook, and I will also put it on the website if I didn't already. And yeah, I'll try to clean up. I will make a new version tonight to clean up, add a few more comments. But you can also see there is a README on this project where I kind of re-explain all that I explained to you today. So you can take a look. Okay, and if you have any problems of installation of dependencies, etc., don't hesitate to just send me an email or ask me. Okay. So this was for the practice. Oh yeah, and I just wanted to show you a last thing. So remember, we talked about the 1D like elementary cellular automaton, but we said that it's very easy to extend this to an arbitrary number of states, an arbitrary number of neighborhoods. So I did implement also that. So this, you can go look at the implementation, is the class general CA1D. And so it takes, again, a Wolfram number, which can now, okay, I don't remember the value. We computed last time. It can take a huge value. And then it has two other values, which are R and K. So R is the radius of the neighborhood, and K is the number of states. So here we'll be looking at cellular automaton that has a neighborhood of radius 3 with 3 states, 3 possible states. So let's see at what does it look like. And again, I have the same keys, so you can change the rule and delete the full thing. So let's see it. So in this case, remember, so if I consider general cellular automata, we'd add like 10 to the 100 possibilities. So these ones are outer holistic, if you remember what it means. So we only compute the sum of the neighbors. Okay, so this is one example. Then I can change the rules. And here the behaviors are, the colors are kind of random. So there are 3 possible states. So you have 3 possible colors. And yeah, you can play with this, find all the possible kind of behaviors. See, most seems chaotic. So you quite often find ones which are interesting. So this one, I can't say if it's chaotic or periodic. This one is obviously periodic. And yeah, this one looks pretty cool. Yeah, I'll let you play, because there are literally like, I don't know how many hundreds of thousands of possible rules. So you're for sure the first person who looks at these dynamics when you run this. Okay. And this is a few lines of code that you will see. You just have to redefine the step and the way you translate the Wolfram number, but it's very simple. Okay. So let's go back to a bit more theory. And then next time it will be pure presentation of cellular automata. So as we said time and time again, general results for cellular automaton are very few and far between. and often they're the kind of the results that we've seen before. Okay, it's completely undecidable. But there is one result which is, it's not to say extremely useful for artificial life, but I find it's a very nice result also philosophically. And it allows you to say some small thing about this real self-reproduction. So I wanted to mention it. And the proof is very beautiful and very simple. So these results concerned, the so-called Garden of Eden configurations. Okay, so what is a Garden of Eden configuration? So you might be able to guess from the name. So the configuration, a Garden of Eden configuration, or GOE, for a cellular automaton, is a configuration that has no parent. Okay, so it's a configuration that you cannot find any configuration of the CA that when you evolve it once, it gives this configuration. So what do we call it, Garden of Eden? Well, according to the Bible, the Garden of Eden was kind of like the start of everything. Okay, I'm not an expert on the Bible, but that's kind of the idea I have. It was the initial condition of the world. And so, of course, the initial condition doesn't have a predecessor, right? It is the start. Okay. So the Garden of Eden configuration for a CA, when you start a simulation, you know that all the possible configuration that you get after the first one cannot be, by definition, Garden of Eden configuration, because they have a predecessor. But the initial one might be. Okay, you might choose a configuration which is impossible to obtain aside from initial condition. Okay, so the Garden of Eden configuration is a statement about the full world of the cellular automaton. And usually when you do this kind of theoretical things, the world of the cellular automaton is infinite. So it's much nicer to work with finite region. And so there is a notion for that, which is the orphan. Okay, so the orphan is a finite region of the cellular automaton, which has no predecessor, no matter how the rest of the space is filled. Okay, so I just say, you have this configuration, then I draw for you a square, and I say, okay, if I need to have this square here, you cannot find a predecessor, no matter what you do. Yeah, it's very similar to the Garden of Eden. The difference is that I can take the orphan, it's finite, and put it inside any configuration, and this will make it a Garden of Eden configuration. Right, so that's what I say here. Given an orphan, it's trivial to build a Garden of Eden configuration. You can just take the orphan, put it somewhere, and then choose anything else as you want. It's a valid Garden of Eden configuration. One can show as well, and look at this proof only if you're very mathematically inclined and you took a course in topology, because otherwise you cannot understand it. That the converse is also true. So if you have Garden of Eden configuration, so infinite configurations which have no predecessor, you can show that you necessarily have one which is finite. But the way to prove it is not very illuminating. As I said, it's just some theorem from topology, and it proves it, but it's not very interesting. So why are Garden of Eden configurations interesting for a life? As I said, not so many reasons. But there are some minor connections which you can make with this Garden of Eden configuration. So these GOEs mark some kind of irreversible checkpoint. Okay, so they can never be reached again. Okay, yeah, so this is not so relevant because it can only appear in the initial condition. So kind of maybe forget about this. But the one which I'm more interested about is this second point. So if you know that orphans exist, you know you cannot have universal constructors. Okay, it's impossible to construct these configurations. So in particular, you cannot have like a constructing arm that constructs whatever you want. Okay, you can construct maybe a subset of the things, but you cannot construct. So in particular, for example, it would be nice to see in the automaton 110, maybe the setup to make a Turing machine is itself a Garden of Eden configuration. And so that way you know that you will not have real reproduction. You cannot just get this state again. Okay? And then you might argue, okay, but when I self-reproduce, I don't get the exact same state again. I get twice the same state. But okay, you can then say, okay, what about if this state is an orphan? Then you definitely cannot construct it. Okay. So yeah, if the Turing machine is a guardian of hidden configuration, there can be no real self-reproduction. And so one example of this would be you take the von Neumann cellular automaton and you say, you remove the possibility to construct the arrows to the left. It's still a valid state, but you cannot construct them with the rules. So with this constraint, I'm still able to make the von Neumann the von Neumann Turing machine, because I don't need to create any left arrows. If I put them where they need to be, it works. And then you kind of prove that this machine cannot self-replicate, despite the fact that it's Turing complete. Okay. So what are the theorems related to this guardian of hidden configurations? Well, there are two, the Moore and Myhill theorems. And they try to capture the following intuition. So intuitively, the existence of orphans seems to be related to the irreversibility of the evolution rule, right? So when we are looking for a predecessor, what we are trying to do more or less is invert the arrow of time, right? Go backwards one time step. So of course, if your rule is reversible, well, there are no guardian of hidden configurations, right? Given any state, I can just apply the reverse rule and go back one time step and find what is the predecessor. So there is this feeling that the existence of orphans is related to irreversibility. So we would like to say, if the rule is irreversible, then there must be orphans. And that's kind of true, but not quite. So if the rule is not reversible, it certainly means that two configurations give the same result, okay? If each configuration give a different result, well, you can just make a list of the configuration and then you have your inverse, okay? So if it's not invertible, you necessarily have this collision. So two parents give the same child, and so when you want to go back from this child, you don't know because you have two possibilities, right? Irreversible. And so with this, you can argue that there should be orphans or GOEs, right? Because you have two parents that give the same child, so there may be one child which is left off, which has no parents, because the two parents gave the same child. And that's kind of the intuition, which is a correct intuition. But as we will see, it's not so clear to make the argument. It's not so straightforward. But that's what we'll try to do. So the theorems try to formalize this intuition. Okay. So let's us first define another thing, which are twin patterns. So two finite patterns are twins if they can be swapped for one another without altering the state in the next time step. Okay. So for example, here I have A and B, which are twins. What does it mean? It means that if I take any configuration with A in this position and then any configuration with B in this position, it will yield the same thing after one time steps. So twins are two such patterns, A and B. Okay. So the guardian of hidden theorem of Moore and Myhill states the following. If you have a cellular automaton which has orphans, this is equivalent to say that it has twins. So this is kind of the intuition, right? These two states go to the same child. So there must be one child which is left out. And so we have orphans. Here, we must be careful, okay? By Euclidean CA, I just mean that a cellular automaton which lives on an Euclidean space. Okay, if you don't know about Euclidean space is the normal space that we have, okay, where the shortest path between 2 points is a straight line. You could think about putting cellular automata on curved spaces, like on a sphere or on a hyperbola, etc. And this theorem might not hold for these. And we'll see why very quickly. So, yeah, so we'll show the one of the two directions. The two directions are kind of similar in the arguments, but the most interesting direction, I think, is the one which says that whenever you have twins, then you have orphans. Why is that? Is because usually finding twins is much easier than finding orphans, and I can show it to you very easily. So let's look at these two configurations. In the von Neumann CA, it's trivial to find twins, right? So these two configurations, if I evolve them by one time step, they will give the same thing, right? This one will just remain as it is, whereas this one, the excitation will just disappear because they are countering each other, so they will evolve to the same state. Okay. So here, notice that I put some kind of insulating layer in this twin, just in case. So usually it's important to put insulating layer because by twin we mean that I should be able to insert this anywhere and still have that they evolve to the same thing. So here, when I was kind of making this example, I was a bit scared to just take these two states, just the two squares, because I was scared that but maybe if around it I put something which kills this blue light, then this excitation might go and create some state which is not created here. It turns out that in this case it's not true. Okay. Also, just these two states are twins. But often when you find twins, for example, in the game of life, it's useful to have this insulating layer to be sure that you're not kind of corrupted from the outside. Okay. So for example, in von Neumann, okay, I said usually twins are easier to find than orphans, but in the von Neumann, it's not too hard to find an orphan. And so you can see that this state here is an orphan. Okay, why is it an orphan? Because we need to find a predecessor, right? If we find a predecessor, then it's not an orphan. So here we need to show that there is no predecessor. But okay, we have this confluent state, which is on. Okay, how do the confluent state turn on? If it receives an excitation. But obviously here, all the paths to receive an excitation are closed. And in one time step, I don't have time to destroy this arrow and then fill an excitation in. So it's clear that there is no predecessor to this state. Right? So you cannot have a state that evolves to this. And so this is an orphan. Okay. So in particular, right, if you start with a machine that has this kind of state, you know that it will not be able to reproduce itself perfectly, right? Not with the excitation. Of course, if there is no excitation, if you have an orphan with no excitations, then with this we prove that, if you have a configuration which has no excitations, this we proved that it cannot be an orphan because we can design, no, it could still be an orphan because the orphan is in one time step. Let me see. Okay, so I'm not too sure about these configurations. No, we proved that it's not an orphan because we can construct them with the constructor, so it should be fine. Okay, so the sketch of the proof. What is it? So we're gonna want to exploit this fact that we have twins, so two configurations that gives the same thing. And then the argument will go as follows. So we'll try to count the number of predecessor and the number of possible children. And we'll see that there are not enough predecessors for the number of children. So there must be children without predecessors. So we start with a 1D CA because it's just simpler. You can make the argument for any dimensional CA. So the 1D CA has k states and a neighborhood radius of R. So the idea is as follows. So we know two configurations that map to the same state. We will show by counting that there are configurations which are missed when evolving any pattern, thus orphans. Okay, so we begin. First, we count the number of output configuration or the number of possible children. Then we bound the number of distinct predecessors. Distinct input predecessors. If the number of predecessor is lower than the number of children, then some children will be missed necessarily, and so we have orphans. Okay. So you might say, okay, this is super simple. Why is it so difficult? So the main difficulty is that when you have a children which is size D, the predecessor are generally bigger, right? Because you have this radius of interaction. So in general, you have much more predecessor than children. So it's very hard to argue that you have more children than predecessors. So that's why we must be very, very clever. Okay. So we start. What is our assumption? Our only assumption is that we have two twins, A and B. So let's assume, we can always assume that they fit on a tape of section N, right? The two twins might not be the same size, but we can always put some garbage and cap it off. Because of the property of the twins, this is still two twins. So we start with this. We have A and B, configuration of length N. When they evolve one step, they go to C, the same one. Great. So now we consider a tape of length T times N. So we take kind of the size of our twin and we repeat it T times. This will be our children, right? Our possible children. And obviously there are S to the Tn possible such tapes, because for each square you have S possibilities, the number of states, and then you have Tn squares. Okay, so this is the number of possible distinct, of possible distinct children of size T times N. Okay, so now we're going to count the predecessors. So we want to estimate how many different tapes. Let me see. Yeah. So we want to. No. We will estimate. We will estimate the number of predecessor, which gives different children. Okay, so we look at the number of predecessors. Okay, the number of predecessors you can compute is the same as the number of children. But here we will argue that, okay, if two predecessors give the same child, okay, they give the same thing. So we don't count twice the predecessors that gives the same child. So how do we do this? So first of all, we need to look at the size of the predecessor. So we said that our cellular automaton has a radius r. So when we have a children here, a child that has size T times N, the potential predecessors, or at least the cells that will influence the cells here, will be of this size, right? We need to add a radius on both sides because that's the interaction length. So our potential predecessors, which can give potentially distinct children, have size T times N plus 2r. Great. So here we are even more generous, right? We even allow the predecessor to be longer. Okay, instead of capping here to r, we'll say we'll increase it and say that we add n on both sides. Okay, we're allowed to do this because we're trying to bound from above the number of predecessors. Here we are just assuming a bigger pool of potential predecessors, so it only makes things worse for us. Okay, so the predecessors are in a tape of length n times t plus 2. Good. So now what do we want to do? So we want to count the number of predecessors which we give rise to distinct children. So if you do this very naively, you would say, okay, if I know nothing about the cellular automaton, I cannot assume anything about the predecessors. And so there are S to the n t plus 2 potential predecessors, and potentially they all give different children. Okay, actually, it's not true, right? Because the children is smaller, but you cannot assume anything about those, okay? So you would get S n t plus 2 potentially distinct predecessors, and that's it. But now, we know we have these two twins, okay? So we should use that when counting in the distinct predecessors. So we know that when we interchange A and B in a predecessor, it does not change the child that they produce, right? So when we count the predecessors, we can count the predecessors only that contain the pattern A. Okay, it's useless to count the predecessors which contain the pattern B because they give the same child. So here we are doing a double counting. So we want to get rid of these B containing predecessors. Okay, so this changes the way we count the distinct predecessors. We know that it will be at most the number of predecessors that contain only A. So what is this number? So we have T plus 2 sections of length n. Okay, so each block size of length n can be in S to the n configurations, right? So it's length n, S choices for each cell, S to the n. But now we know that we should not consider the configuration B. Okay, there is one configuration which is useless to count. Okay, okay. So what can we say? Okay, we can say that for each block of size n, instead of considering S to the n, we consider S to the n minus 1 distinct predecessors. Okay, this seems extremely small, right? All we are doing, we're saying that for each block of length n, we have one less predecessor. That's all we can say. Okay. So what is our upper bound for the number of predecessors that yield distinct outputs? Well, we choose Sn minus 1 for each block, and we have T plus 2 blocks, right? And so now what we want to do, if we have orphans, it means that we will have less distinct predecessor than distinct successors, okay? So we will have orphans if this inequality is true for some T, right? And you can check, this inequality will actually be satisfied if you take a T which is big enough. Okay, it's not immediately obvious because here you have S to the Tn. Here you have a smaller number, but it's to a higher power, so it's not clear. Okay, if you take the log of this inequality, you can rewrite it in this way. And so you know that log of Sn minus 1 is smaller than log of Sn, strictly smaller. And here what we are doing, we are taking log to the Sn minus 1 and adding a small contribution, right? Because we divide by T. So if T is sufficiently high, this contribution is negligible, and so log of Sn minus 1 will be smaller than this. So we just showed with this extremely crude bound, I want to underline that we basically did nothing, right? We move one possible configuration for each block, and yet this is enough to show. Of course, you will need a T, which is humongous, right? Because the log here grows very slowly, so the difference between these two will be very small. But for sufficiently large T, you will have an orphan. Your orphan will be extremely big, okay, so it's not constructive as a proof, but you know that you have one. So we're able to show that you do not have enough predecessors to fill all possible children, and thus that you have orphans. And so when you want to prove the opposite, so whenever you have orphans, you necessarily have twin, you kind of do the same sort of counting argument, but in reverse, right? So you use the fact that some children don't have parents to cap the number of possible distinct children, etc., etc. So yeah, so just a thought. So remember I said Euclidean, okay? So the way this proof worked in a how do you say, in a more high level way is that sure, we have more predecessor than children because of this radius of interaction. But if I consider bigger and bigger children, the border, the radius of interaction is negligible with respect to the size of the children. And that's why we just need to remove one possible predecessor to be able to make the argument. And why is this true? This is true because the way that the border grows is slower the way than the volume grows. So if we made the argument for 2 DCAs, we would have taken a square with kind of border with a radius. And as the square grows bigger, the area of the square grows with r squared, squared to the size of the square, whereas its perimeter grows linearly in the size of the square. And that's what allows us to make the argument. So is this T plus 2, right? The number of predecessors is proportional to T plus 2, but the plus 2 is not much more. right? In 2D, it would have been t squared plus 4t. So the t grows less than the t squared. And that's when you get problems in Euclidean space, or in non-Euclidean spaces. So because of the curvature, you could have that kind of the border of the square grows as fast as the area of the square, simply because if your square is in the middle and then the border is stretched, and that's why you cannot make the argument in some curved spaces. Okay, that's just a curiosity. And so to finish, yeah, some fun thoughts about the Guardian of Eden configurations. So suppose we figure out with certainty at some point, maybe Wolfram is right and the fundamental theory of physics is just some cellular automaton. If information is not destroyed, we could kind of deduce the state of the universe at an earlier time, right? Kind of like we're doing with the Big Bang. But we would be able to tell, right? If you know the rules of evolution, you're able to tell if a state is a Guardian of Eden or an orphan, according to the physics law, okay? So we could kind of determine, okay, the state at the Big Bang is actually a Guardian of Eden configuration. So it literally is the beginning of time. There is no other possibility, right? You prove that it's the beginning of time. So that's kind of a nice thought. But of course, there are many conditions. We need to be a cellular automaton. We need to be in Euclidean space, etc. So no, Euclidean space is not necessary, but it's useful to show Guardian of Eden. So another thought, which is very similar. So if we are being simulated in a computer, it's impossible to tell how long you are being simulated for, right? Because they can just start the simulation now, but they start your brain with all the memories of 10 years ago. So you feel like you at least lived 10 years, but it doesn't mean that you did. It just means that you have the memories that you did. Right, the memories could be fake. So each time you think, okay, all you know is that the moment that you think, okay, now I'm thinking, you're actually being simulated, but you don't know anything about your past. So for example, if you were to identify a moment in the past, which for some reason is a Guardian of Eden configuration, then you know that the simulation started at least after this moment, right? So you know where the beginning of the simulation is somehow. And so if you're interested in these kind of philosophical questions about simulations, etc., you should definitely read Permutation City, which is a book by Greg Egan. And that's where these examples come from. And it's a very, very interesting book. It also talks a lot about artificial life, etc. So if you like science fiction, this is a very good book to read. So yeah, so we have 5 minutes left. So this, yeah, I kind of was unsure if I wanted to mention this, but let me mention it very fast. So far, the interesting automata that we have seen seem irreversible, right? So usually you always have twins. And in fact, it's very rare to have reversible cellular automata. They're extremely rare. So you might ask yourself, do we need irreversibility to get interesting or complex dynamics? Okay. So if you look to that from a physics perspective, you have something called the Landauer bound, which tells you that if you want to flip some bit, so if you want to record some information, there is a minimum amount of heat that you need to dissipate. Okay, it's impossible to flip a bit without creating some heat, or in other words, without increasing the entropy of the world. And that's actually, I mean, it's not proven, nothing is ever in physics, but people believe really this to be true. And so looking at this Landauer bound, you might be tempted to say, okay, yeah, you need to be reversible to do computations because you need to increase the entropy, and then, okay, you cannot go back whenever you increase the entropy. Yes, and so what I wanted to say is that it's not really true. So there is something, so the usual computation gates like C0, for example, are irreversible. Okay, so simply because, okay, you take 2 bits and you, you take 2 bits and then you get out 1 bit. So of course, from this 1 bit, you cannot deduce the 2 bits. And so, yeah, it seems that it's kind of a correct statement. But then you have something called Toffoli gates, I think. So Toffoli asked this question about irreversibility and computation. And he actually realized that it's true, the OR gate or the NOT gate are irreversible, but he designed these Toffoli gates, which takes 4 bits and output 4 bits. And what happens is that if you look at one of the 4 bits, so let me pull out the picture if I can. Yeah, I forgot to prepare this part of the course, but it was just some small mention. Yeah. So essentially, yeah. So we have this truth table. So as input, you get input 2 bits and output 2 bits. And so if you look at the last column here, what this column does is the XOR, probably. No, the CNOT. Wait, yeah, it's the CNOT gate, right? So if the 2 bits are different, you get 1. Otherwise, you get 0. So if you look at the output, if you look at only one of the outputs, you do the CNOT gate, which you can use to do computations. But you have also this extra output, which is essentially garbage. You don't use that in your computations. But if you want, now you can use this garbage output to reverse all the gates, right? So now you make any gate irreversible by adding some extra bits of garbage. And so it seems that indeed, when you do computation, you can do everything in an irreversible manner using these Toffoli gates. And that's true. And that's also true for cellular automata. I don't have the picture there, but for any cellular automaton in 2D, one way to make it reversible is to do this Toffoli gate treatment. So you add a 3rd dimension, and at each interaction, you extract some garbage in the 3rd dimension. And if you look at the garbage and the 2D slice, you're able to reverse everything. So you could take the game of life and do this treatment, and this will give you a 3D cellular automaton, which is reversible, but which is also interesting, okay? And how are these things resolved? So this Landauer bound you need to be irreversible. Well, the answer is that when you use these Toffoli gates, you get all this extra garbage additionally to your computation. And the more irreversible your computation is, the more the garbage is really tangled, right? It's some like completely random, okay? So in a way, yes, technically you are irreversible, but the garbage that you pull out, it's so entangled that you still increase the entropy of the world, right? Because the garbage is really difficult to untangle without going through the steps one by one behind. And so in the end, okay. The better way to say it is that you can do everything reversibly, but if you want to do some sort of computation, you need to increase the entropy somewhere in your system. So you need to kind of mix up some information somewhere else. And the example of the Toffoli gate is a concrete example. So this was just to connect to this irreversibility with the Guardian of Eden, but yeah, it's just a thought. And I think we can stop here. Yeah, perfect. And so next week, we'll be looking at more discrete CAs, so the Baricelli cellular automaton, 2D binary CAs, and potentially the lattice gas cellular automata. And after that, we'll be done with the first part of the discrete CAs, and we'll go to reaction diffusion model to see what happens in the continuous. Okay, any questions before I leave you? Otherwise, yeah, you're free to go. Okay.